Right now, at this exact moment, you are staring into a screen. You think you are safe. You think the walls around you are solid, permanent, real. But here is the truth. They do not teach you in school. Somewhere in the universe, right now, there is a structure so massive, so violent, so incomprehensibly dense, that if you could see its true scale, your mind would break trying to process it. A black hole. And not just any black hole. We are talking about monsters that make our sun look like a grain of sand on an infinite beach. We are talking about objects that bend the fabric of reality itself, that consume light, that delete information from existence. You have heard the name. You have seen the blurry orange images from the Event Horizon telescope. But you do not understand what you are looking at. You cannot. Because the human brain did not evolve to comprehend structures measured in billions of kilometers, masses measured in billions of suns, gravitational forces so extreme that time itself becomes a weapon. Tonight, that changes. We are going to confront the true scale of black holes, and when you understand what they really are, when you grasp the horrifying magnitude of these cosmic predators, you will never look at the night sky the same way again. You will realize how small you are, how fragile, how utterly insignificant. Let us start with you, your body, the thing you think you know. You are made of approximately 7 octillion atoms. That is a 7 followed by 27 zeros. 7 octillion tiny particles, vibrating, bonded together in patterns so precise that you can think, breathe, exist. Each atom in your body has a nucleus at its center, protons and neutrons packed together, and here is where scale begins to break your intuition. That nucleus, the core of every atom in your body, is 100,000 times smaller than the atom itself. If you scaled an atom up to the size of a football stadium, the nucleus would be a marble sitting at the 50-yard line. The rest? Empty space. You are mostly nothing, mostly void. Your skin, your bones, your brain. All of it is 99.9999% empty space, held together by electromagnetic forces you cannot see or feel. Now zoom out. Your body is about 1.7 meters tall. Maybe less. Maybe more. It does not matter. You are a biological machine occupying roughly 0.06 cubic meters of space. You live on a planet with a diameter of 12,742 kilometers, Earth. A rock spinning through the void at 107,000 kilometers per hour around a star we call the Sun. The Sun has a diameter of 1,392,000 kilometers. You could fit 1.3 million Earths inside the Sun's volume. And the Sun is average, unremarkable, one star among 400 billion in our galaxy alone. But we are not here to talk about stars. We are here to talk about what happens when stars die. When they collapse, when gravity wins. A star is a war. Gravity pulls inward, trying to crush the star into a point. Nuclear fusion pushes outward, converting hydrogen into helium and releasing enough energy to hold back the collapse. For millions or billions of years, this war is a stalemate. The star burns, it shines, it exists in balance, but fuel runs out, fusion stops, and gravity, patient and relentless, wins. What happens next depends on the star's mass. If the star is small, like our Sun, it swells into a red giant, sheds its outer layers, and leaves behind a white dwarf. A hot, dense ember slowly cooling for trillions of years. If the star is more massive, 8 times the mass of the Sun or more, the ending is violent. The core collapses in less than 1 second. Electrons and protons are crushed together, forming neutrons. The collapse halts when the core becomes a neutron star, a sphere roughly 20 kilometers across made entirely of nuclear material. The outer layers rebound off this incompressible core and explode outward in a supernova, one of the brightest events in the universe. But if the star is even more massive, if it started its life with 20 times the mass of the Sun or more, something else happens, something darker. The core collapses, but it does not stop. There is no force in the universe strong enough to halt the implosion. Neutron degeneracy pressure, the force that creates neutron stars, fails. The core continues to collapse. Smaller, denser, more compact, until it crosses a threshold, a point of no return. The escape velocity at its surface exceeds the speed of light. And at that moment, the object becomes invisible, unreachable, a black hole. Let us be clear about what a black hole is. It is not a hole, it is not empty space, it is the opposite. It is mass, compressed, compacted into a region so small that the density becomes effectively infinite. Imagine taking the Sun, with its diameter of 1,392,000 kilometers, and crushing it down until it fits inside a sphere 6 kilometers across. That is the Schwarzschild radius of the Sun, the size it would need to become a black hole. At that density, the gravitational field becomes so intense that space-time itself curves into a trap. Light emitted from the surface cannot escape, it falls back down. The object vanishes from the universe, leaving behind only its gravitational signature. The smallest black holes we know of are called stellar mass black holes. These form from the collapse of massive stars. They typically range from 5 to 100 times the mass of the Sun. Let us take an example. V616 Monocerotis, a star system about 3,000 light-years from Earth. In 2006, astronomers confirmed that this system contains a black hole with a mass of approximately 9.6 solar masses. 9.6 times the mass of our Sun, compressed into a sphere with a diameter of roughly 57 kilometers. That is smaller than most cities. Manhattan is roughly 22 kilometers long. You could fit this black hole, an object containing the mass of nearly 10 suns, inside the length of Manhattan twice. And yet, from that tiny volume, it exerts a gravitational pull strong enough to hold a companion star in orbit, pulling gas off that star's surface, heating it to millions of degrees, causing it to emit X-rays we can detect across 3,000 light-years of space. But stellar mass black holes are nothing. They are footnotes, appetizers, because at the centers of galaxies, something far more monstrous lurks. In the early 1960s, astronomers discovered quasars, quasi-stellar radio sources, distant points of light that looked like stars but emitted radio waves with intensities no star could match. As observations improved, the truth emerged. Quasars were not stars. They were galaxies. Entire galaxies shining with the light of trillions of suns. All that energy pouring out from a region smaller than our solar system. The only explanation that made sense was terrifying. At the center of each quasar there had to be a supermassive black hole. A black hole with the mass of millions or billions of suns, feeding on gas and stars, converting matter into energy with an efficiency far exceeding nuclear fusion. For decades, this was theoretical, but in the 1990s, observations confirmed it. Every large galaxy we can study in detail has a supermassive black hole at its center, including ours. At the heart of the Milky Way, 26,000 light-years from Earth, sits Sagittarius A star, a black hole with a mass of approximately 4 million times the mass of the Sun. 4 million solar masses compressed into a sphere with a diameter of roughly 44 million kilometers. That sounds large. It is roughly 30% of the distance from the Sun to Earth. But remember, this is 4 million suns worth of mass. If you could somehow gather 4 million copies of our Sun and place them side by side, they would stretch across billions of kilometers. Sagittarius A star fits all that mass into a space 1/3 of an astronomical unit across. And Sagittarius A star is small, modest, quiet, a dwarf among supermassive black holes. In April 2019, the Event Horizon Telescope collaboration released an image that went viral across the planet, a blurry orange ring surrounding a dark center. This was M87 star, the supermassive black hole at the center of the galaxy Messier 87, located 55 million light-years away in the Virgo cluster. M87 star has a mass of approximately 6.5 billion solar masses, 6.5 billion times the mass of our Sun. Its event horizon, the boundary beyond which nothing can escape, has a diameter of roughly 38 billion kilometers. That is about 255 times the distance from the Sun to Earth. If you placed M87 star where our Sun is, its event horizon would extend far beyond the orbit of Neptune, beyond the Kuiper belt, reaching into the Oort cloud. 6.5 billion suns. Imagine trying to visualize that. You cannot. Your brain lacks the framework. So let us try a different approach. Let us talk about consumption. M87 star is actively feeding. Gas from the surrounding galaxy spirals inward, forming an accretion disk. As the gas falls toward the event horizon, friction heats it to billions of degrees. The disk glows. It screams electromagnetic radiation across the spectrum, and from the poles of the black hole, jets erupt, beams of matter and energy moving at 99% the speed of light, stretching across 5,000 light-years of space. These jets are visible in radio telescopes. They are monuments to violence, to power, to the transformation of mass into energy on a scale that makes nuclear weapons look like firecrackers. But M87 star is not the largest black hole we have discovered, not even close. In 2011, astronomers announced the discovery of a black hole at the center of the galaxy NGC 4889, roughly 336 million light-years from Earth. This black hole has a mass of approximately 21 billion solar masses, 21 billion suns compressed into a region with an event horizon diameter of roughly 246 billion kilometers. That is 1,600 times the distance from the Sun to Earth. At that scale, the black hole's event horizon alone would stretch across a region larger than our entire solar system many times over. And then there is TON 618, a hyperluminous quasar located approximately 10.4 billion light-years away. The black hole powering this quasar has an estimated mass of 66 billion solar masses, 66 billion times the mass of our Sun. Its event horizon would have a diameter of approximately 773 billion kilometers. To put this in perspective, light takes roughly 3 days to cross that distance. 3 days. Traveling at 300,000 kilometers per second, it would take light 72 hours to journey from one side of this black hole's event horizon to the other. This is not a stellar object. This is a structure, a void, a predator so large that entire solar systems could fall into it and vanish without causing a ripple. You still do not understand the scale. Let me make it personal. Let us say you are standing on a planet orbiting a star near TON 618. You look up at the night sky and you see it. A black circle covering a portion of the sky. Not a small dot, not a distant star, a hole in reality. Surrounded by a glowing accretion disk, brighter than 1 trillion suns. The light from that disk, if you were close enough to see the black hole with the naked eye, would cook you alive. The radiation would sterilize your planet's surface in seconds. The tidal forces, the difference in gravitational pull between the side of your planet facing the black hole and the side facing away, would rip your world apart long before you got close enough to see anything. You would die. Your planet would die. And the black hole would not notice. It would continue feeding, consuming stars, gas, light, information, growing larger, more massive, more dominant. And yet, TON 618 is not the limit. In 2015, astronomers discovered a black hole in the galaxy Holm 15A, located approximately 700 million light-years away. Initial estimates suggested this black hole might have a mass of 170 billion solar masses, 170 billion suns. Though later refinements adjusted this estimate downward to around 40 billion solar masses, the initial calculation reveals something critical. We do not know where the upper limit is. We do not know how large black holes can grow. Theory suggests there might be a maximum, somewhere around 50 billion solar masses, where the black hole becomes so massive that it disrupts the galaxy around it, cutting off its own food supply. But this is speculation, math on paper. The universe does not care about our theories. Let us ground this in something you can visualize. Imagine you are holding a basketball. This basketball represents Earth. On this scale, the Sun would be a sphere roughly 22 meters across, about the size of a large house. Now scale up a black hole. Sagittarius A star. The black hole at the center of our galaxy would be roughly 8.7 kilometers across on this scale. Not its mass, its event horizon. The boundary of no return, 8.7 kilometers. You could walk across it in 2 hours. But remember, this sphere contains 4 million suns worth of mass. M87 star, on the same scale, would be roughly 755 kilometers across, the distance from New York City to Detroit. TON 618 would stretch approximately 15,300 kilometers. That is larger than Earth's diameter, an event horizon larger than the planet you are standing on. And this is just the boundary, the point where escape velocity equals the speed of light. The singularity, the actual collapsed core where all the mass resides, is theoretically infinitesimal. A point, zero volume, infinite density. Reality breaks down at the singularity. Our equations fail. General relativity predicts infinite curvature. Quantum mechanics screams in protest. Something is wrong with our understanding, but we do not know what. Now let us talk about what happens at the event horizon. This is the defining feature of a black hole, the Schwarzschild radius. Named after Karl Schwarzschild, the German physicist who in 1916, while serving in the German army during World War I, derived the first exact solution to Einstein's field equations of general relativity. Schwarzschild was stationed on the Russian front, suffering from a painful autoimmune disease, and yet he managed to solve one of the most complex mathematical problems in physics. He sent his solution to Einstein, who presented it to the Prussian Academy of Sciences. Schwarzschild died less than 4 months later. He never lived to see what his equations predicted. He discovered that if you compress enough mass into a small enough space, you create a region where the curvature of space-time becomes so extreme that light cannot escape. The escape velocity exceeds 300,000 kilometers per second. And since nothing can travel faster than light, nothing escapes. Ever. The event horizon is not a physical surface. It is not a wall. It is a mathematical boundary, a point of no return embedded in the geometry of space-time. Cross it, and your future becomes constrained. Every path forward, every possible trajectory leads inward, toward the singularity. There is no turning back. Not because you lack the engine power, not because you did not bring enough fuel, but because the structure of space-time itself has changed. The dimension we call forward in space has become the dimension we call forward in time. Inside the event horizon, falling toward the singularity is as inevitable as moving forward in time is outside. You cannot avoid it any more than you can avoid tomorrow. But the size of the event horizon determines how you die. And this is where scale becomes personal, lethal, intimate. If you fell toward a stellar mass black hole, something like V616 Monocerotis, with its 9.6 solar masses and 57-kilometer event horizon, you would die long before you crossed the boundary. The process is called spaghettification. Tidal forces. The difference in gravitational pull between your head and your feet. Gravity follows an inverse square law. It weakens with distance. If you are falling feet first toward a black hole, your feet are closer to the singularity than your head. They experience stronger gravity. They accelerate faster. The difference in pull stretches you. At first, it is subtle, uncomfortable, like someone is pulling on your legs, but as you get closer, the tidal gradient increases exponentially. Your bones stretch. Your muscles tear. Your blood vessels rupture. Your body elongates, becoming thinner and thinner, like a string of atoms being pulled apart by the universe itself. You are conscious for some of this. Your brain continues firing, continues processing pain signals, continues existing in a state of agony as your molecular bonds scream under stress. And then, at some point, the tidal forces exceed the electromagnetic forces holding your atoms together. You dissolve, not into pieces, into atoms, into particles, into a stream of matter spiraling down into the abyss. For a stellar mass black hole, spaghettification begins thousands of kilometers above the event horizon. You die in space, outside the point of no return, your remains forming a thin stream of atomized flesh that eventually crosses the boundary and disappears. But here is the paradox. From your perspective, from your reference frame, you cross the event horizon in finite time. Seconds, maybe minutes, depending on your trajectory. But to an observer watching from a safe distance, you never cross. Time dilation, the slowing of time in strong gravitational fields, means that as you approach the event horizon, your clock runs slower and slower relative to the outside universe. To the observer, you appear to freeze. Your image redshifts, the light stretching to longer and longer wavelengths, fading from visible light to infrared to radio waves until you disappear. Not because you crossed, but because the light carrying your image can no longer escape. You are trapped in time, a ghost imprinted on the boundary, fading over eons. But if the black hole is larger, if it is supermassive, the tidal forces at the event horizon are weaker. Tidal force depends not just on mass, but on the gradient of the gravitational field. A larger black hole has a gentler gradient at its event horizon. For M87 star, with its 6.5 billion solar masses and 38 billion kilometer event horizon, you could cross the boundary alive. Unharmed. You would not feel anything. No jolt, no pain, no physical sensation marking the moment you pass the point of no return. You would simply continue falling, looking around, seeing the universe behind you through the increasingly distorted light, while ahead of you, the singularity waits. You would have hours, maybe days, falling through the interior of the black hole through a region of space-time that has no exit, no communication with the outside universe. Until eventually, closer to the singularity, the tidal forces grow strong enough to kill you. Spaghettification happens here too, but later, deeper inside. You die inside the event horizon, where no one can ever know what happened to you. For the largest black holes, like TON 618 with its 66 billion solar masses, you could survive even longer. The event horizon is so large, the tidal gradient so gentle, that you might live for weeks inside the black hole before the singularity's tidal forces finally tore you apart. Weeks. Falling through a space that is not space. A region where every direction is down, where time flows in only one direction, toward the singularity, and you are a passenger on a one-way journey into the ultimate unknown. But let us step back. Let us talk about what this means for scale. For perspective, your body is roughly 1.7 meters tall. A stellar mass black hole's event horizon is 57 kilometers across. You are 335,000th the size of the black hole. On a linear scale, you are invisible, irrelevant. But mass matters more than size. That black hole contains 9.6 times the mass of the Sun. The Sun has a mass of approximately 1.989 times 10 to the power of 30 kilograms. Multiply that by 9.6. The black hole's mass is roughly 1.91 times 10 to the power of 31 kilograms. You have a mass of maybe 70 kilograms. You are approximately 2.7 times 10 to the power of negative 29, the mass of a stellar black hole. That is a decimal point, followed by 28 zeros and then a 2. You are nothing. A rounding error in the gravitational field. Now scale up. M87 star has a mass of 6.5 billion solar masses. That is approximately 1.29 times 10 to the power of 39 kilograms. You are approximately 5.4 times 10 to the power of negative 38 of its mass. Your existence does not register. The black hole's gravity does not notice you. If you fell in, you would not add mass to it in any measurable way. You would vanish, deleted from the ledger of the universe. And TON 618 with 66 billion solar masses is even worse. You are approximately 5.3 times 10 to the power of negative 39 of its mass. The numbers become absurd, meaningless. You cannot comprehend how small you are compared to these structures. You are not even a speck of dust. You are less than an atom is to a planet. You are a quantum fluctuation in a gravitational field that spans hundreds of billions of kilometers. Let me give you another comparison. The Milky Way galaxy contains approximately 400 billion stars. Most of these stars are smaller than the Sun. But let us average them out and say the Milky Way contains roughly 400 billion solar masses worth of stars. Sagittarius A star, at 4 million solar masses, is 1% of the galaxy's stellar mass. It is a tiny fraction, and yet its gravity dominates the galactic center. Stars orbit it at speeds exceeding 5,000 kilometers per second. The star S2, which orbits Sagittarius A star every 16 years, reaches speeds of approximately 5% the speed of light at its closest approach. 5%. That is 15,000 kilometers per second. The star is screaming through space, held in a death grip by an invisible mass that warps space-time into a funnel. Now let us talk about what happens around black holes. The accretion disk. When a black hole feeds, when matter falls toward it, conservation of angular momentum prevents the material from falling straight in. It spirals, like water circling a drain. The infalling matter forms a rotating disk of gas, dust, and plasma. And in this disk, something extraordinary happens. Friction. The inner edge of the disk rotates faster than the outer edge because it is closer to the black hole, experiencing stronger gravity. Material rubs against material. Atoms collide. Energy dissipates as heat. The temperature rises. For a stellar mass black hole, the inner edge of the accretion disk can reach temperatures of 10 million degrees Celsius. The gas glows in X-rays. For a supermassive black hole, the temperatures are lower because the disk is larger and the material is spread out over a greater area, but the total energy output is staggering. Consider M87 star again. Its accretion disk, though cooler than a stellar mass black hole's disk per unit area, extends across hundreds of billions of kilometers. The total luminosity, the total amount of energy radiated by the disk, is equivalent to trillions of suns. Trillions. If you could somehow bottle the energy output of M87 star's accretion disk for 1 second, you would have enough energy to power human civilization for billions of years. And this energy is the byproduct, waste heat from matter falling into the abyss. The black hole itself is converting mass into energy with an efficiency of approximately 10%. Nuclear fusion, the process that powers stars, converts roughly 0.7% of mass into energy. Black hole accretion is 14 times more efficient than the process that makes the sun shine. This is the most efficient energy extraction mechanism in the known universe. Matter falls in. Mass becomes energy, and that energy lights up galaxies. But the accretion disk is not the only mechanism by which black holes announce their presence. There are the jets, relativistic jets, beams of matter and energy launched from the poles of spinning black holes at velocities approaching the speed of light. The mechanism is not fully understood, but the leading theory involves magnetic fields. As the accretion disk rotates, it drags magnetic field lines with it. These field lines become twisted, wound up like a spring under tension. Eventually, the magnetic energy becomes so concentrated near the black hole's poles that particles are accelerated to extreme velocities and ejected in narrow beams. These jets can extend for thousands or even millions of light years. They punch through the interstellar medium, through intergalactic space, creating enormous lobes of radio emission visible across cosmological distances. M87 star has a jet, a beam of plasma erupting from its north pole, stretching across 5,000 light-years of space. 5,000 light-years. To put this in perspective, the distance from Earth to the nearest star, Proxima Centauri, is 4.24 light-years. M87 star's jet is more than 1,000 times longer than the distance to our nearest stellar neighbor. And this jet is moving. Material within the jet travels at approximately 99% the speed of light. At that velocity, relativistic effects dominate. Time dilation. Length contraction. The particles in the jet experience time passing more slowly than we do. For them, the journey across 5,000 light-years takes objectively less time. But for us, watching from outside, the jet is a monument, a scar carved across the universe by an object we cannot see, only infer from the violence it creates. And here is the disturbing part. These jets, these relativistic beams, are destructive. If a jet from a supermassive black hole were pointed at Earth, if we happen to be in the line of fire, the radiation would sterilize our planet in seconds. The gamma rays, X-rays, and high-energy particles would strip away our atmosphere, boil our oceans, and scour the surface clean of life. There would be no warning. Gamma rays travel at the speed of light. We would see the jet at the same moment it killed us. And the black hole, 65 million light-years away or more, would not notice. It would continue feeding, continue launching plasma into space, indifferent to the civilizations it erased. Let us return to scale. To the question of size, we have established that black holes range from stellar mass objects 57 kilometers across to supermassive monsters with event horizons spanning hundreds of billions of kilometers. But how do we measure them? How do we know these numbers are real? Because black holes are black. They do not emit light. They are invisible. Observing them requires indirect methods. We measure their mass by observing the objects around them. Stars orbiting the galactic center. Gas spiraling into an accretion disk. Gravitational lensing, the bending of light from background objects. Each method provides constraints, limits, estimates, and from these observations we calculate mass. And from mass, using the Schwarzschild equation, we calculate the event horizon radius. The math is elegant. Simple. The Schwarzschild radius is equal to 2 times the gravitational constant times the mass, divided by the speed of light squared. Plug in the mass of Sagittarius A star, 4 million solar masses, and you get an event horizon diameter of approximately 24 million kilometers. Plug in 66 billion solar masses, and you get TON 618. But there is another way to measure black holes. A new way. Gravitational waves. In September 2015, the LIGO detectors in Louisiana and Washington state recorded a signal. A chirp. A ripple in spacetime caused by 2 black holes, each approximately 30 solar masses, spiraling into each other and merging. The event happened 1.3 billion light-years away, 1.3 billion years ago. The black holes orbited each other, moving faster and faster, closer and closer, radiating gravitational waves, losing energy until finally they collided. In the final tenth of a second before merger, they were orbiting each other 250 times per second. 250 times. The velocities exceeded 60% the speed of light. When they merged, the collision converted 3 solar masses worth of energy into gravitational waves. 3 suns. Erased. Transformed into ripples in spacetime that spread outward at the speed of light, crossing 1.3 billion light-years of space, eventually washing over Earth and causing the LIGO mirrors to move by less than 1,000th the diameter of a proton. Since that first detection, LIGO and its partner detector Virgo have observed dozens of black hole mergers. Each merger tells a story. Each one provides data. Mass, spin, distance. We now know that black holes exist across a wide range of masses. We know that they merge. We know that stellar mass black holes are common. And we know something else, something unexpected. LIGO has detected black holes with masses in the range of 50 to 100 solar masses. Black holes that should not exist. According to stellar evolution theory, stars massive enough to produce black holes above 50 solar masses should lose most of their mass through stellar winds before they collapse. They should not be able to create black holes that heavy. And yet, the detections are real. The data is clear. Either our models of stellar evolution are wrong, or these black holes formed through a different mechanism. Perhaps they are the result of previous mergers, black holes that formed from the collapse of massive stars, then merged with other black holes, growing larger over time. Or perhaps they formed in the early universe, in regions of extremely high density, where physics operated under different conditions. We do not know. The universe has surprised us. Again. But gravitational wave detections have revealed something even more profound. They have allowed us to test general relativity in the most extreme conditions imaginable. When two black holes merge, the collision creates a single, larger black hole. This final black hole is initially distorted, not spherical. It vibrates, rings, like a bell struck by a hammer. These vibrations, called quasi-normal modes, emit gravitational waves at specific frequencies determined by the black hole's mass and spin. General relativity predicts these frequencies with extraordinary precision, and the observations match the predictions perfectly, within measurement error. This is not just evidence that general relativity is correct. It is evidence that black holes are exactly what the equations say they are. Objects described purely by mass and spin. No hair, no additional properties. Just mass, spin, and charge, though charge is likely negligible for astrophysical black holes. This is the no-hair theorem. A black hole is defined entirely by three numbers. Everything else, all the information about what fell in, is lost, erased, deleted from the universe. And this brings us to one of the deepest mysteries in physics, the information paradox. When matter falls into a black hole, information about that matter disappears. Not just the matter itself. Information, the quantum state, the exact configuration of particles and fields that define the object before it crossed the event horizon. According to quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, transformed, but not erased. And yet, black holes appear to erase it. Once something crosses the event horizon, no information about its quantum state can ever return to the outside universe. The singularity crushes it. The horizon traps it. It is gone. This creates a paradox, a contradiction between general relativity, which describes black holes, and quantum mechanics, which forbids information destruction. For decades, physicists have grappled with this. Stephen Hawking originally argued that information is lost. Later, he reversed his position, proposing that information might be encoded on the event horizon itself, stored in a two-dimensional holographic form. Others have proposed that information escapes through Hawking radiation, the quantum process by which black holes slowly evaporate. But no one knows the answer. Not yet. The information paradox remains unsolved. And until we have a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics, we will not know what happens to the information that falls into a black hole. Hawking radiation. Let us talk about this. In 1974, Stephen Hawking published a paper that shocked the physics community. He demonstrated that black holes are not entirely black. They emit radiation. Not from inside the event horizon, nothing escapes from inside. But from just outside the horizon, quantum effects create particle pairs. Virtual particles. A particle and an antiparticle popping into existence from the vacuum, borrowing energy from the universe for a brief moment before annihilating each other. Normally, these virtual pairs exist for such a short time that they are undetectable. But near a black hole's event horizon, something different happens. One particle of the pair can fall into the black hole, while the other escapes. To an outside observer, it looks like the black hole emitted a particle. And to conserve energy, the black hole must lose mass. It evaporates. Slowly. Incredibly slowly. The rate of evaporation depends on the black hole's mass. Smaller black holes evaporate faster. Larger black holes evaporate slower. A stellar mass black hole with 10 solar masses would take approximately 10 to the power of 67 years to evaporate completely. That is 10 followed by 67 zeros. Years. For comparison, the current age of the universe is approximately 1.38 times 10 to the power of 10 years. The universe would need to age by a factor of 10 to the power of 57 before a stellar mass black hole disappeared. And for supermassive black holes, the timescales are even more absurd. A black hole with 1 million solar masses would take approximately 10 to the power of 83 years to evaporate. 1 billion solar masses? 10 to the power of 92 years. These numbers are so large they lose meaning. But the principle remains. Black holes are not eternal. They decay, they die. Given enough time, every black hole in the universe will evaporate, leaving behind nothing but a faint whisper of radiation spread across an ever-expanding cosmos. But the far future is not our concern. Not tonight. We are here to understand a scale in the present. So let us talk about what happens to space-time itself around a black hole. Because a black hole is not just an object with mass. It is a deformation, a wound in the fabric of reality. Einstein's general relativity tells us that mass curves space-time. The sun curves space-time around it, causing Earth to orbit. Earth curves space-time around it, causing the moon to orbit. This curvature is gravity. But these are gentle curves, shallow indentations. A black hole is different. A black hole does not curve space-time. It breaks it, punctures it, creates a bottomless pit where the gradient becomes infinite at the singularity. Imagine space-time as a rubber sheet stretched flat. Place a marble on the sheet. It creates a small dip. Roll another marble nearby, and it will curve toward the first marble, following the contour of the depression. This is gravity. Now replace the marble with a bowling ball. The depression becomes deeper, the curvature more pronounced. Now replace the bowling ball with something infinitely heavy compressed into an infinitely small point. The sheet does not just dip, it tears. It folds in on itself. The depression becomes a funnel with no bottom, and anything that rolls too close does not orbit. It spirals inward and disappears. This is a black hole, a singularity in the manifold of space-time, a defect in the structure of the universe itself. But not all black holes are the same. The Schwarzschild solution, the one Carl Schwarz derived in 1916, describes a non-rotating black hole, a static black hole. But real black holes, formed from collapsing stars or merging matter, inherit angular momentum from their progenitors. They spin. And a spinning black hole is described by a different solution to Einstein's equations. The Kerr metric, named after Roy Kerr, the New Zealand mathematician who derived it in 1963. A Kerr black hole has an event horizon like a Schwarzschild black hole, but it also has another boundary. The ergosphere, a region outside the event horizon where space-time itself is dragged around the black hole, frame dragging. If you were in the ergosphere, you could not remain stationary relative to the distant stars. Space-time itself is rotating, and you would be dragged along with it. Not by friction, not by any physical force, but by the structure of space-time. You would be forced to orbit the black hole simply by existing in that region of space. The ergosphere is not a point of no return. You can escape from the ergosphere. Unlike the event horizon, where all future paths lead inward, the ergosphere still permits outward trajectories. But escaping requires energy, thrust. And here is where the Kerr black hole becomes even stranger. There is a process called the Penrose process, named after Roger Penrose, who proposed it in 1969. If an object enters the ergosphere and splits into two pieces, with one piece falling into the black hole and the other escaping, the escaping piece can carry away more energy than the original object had. The black hole loses rotational energy, its spin decreases, and the escaping fragment gains energy. This is not a violation of conservation laws. The energy comes from the black hole's rotation. But it means that a spinning black hole is a battery, a reservoir of extractable energy. An advanced civilization could, in theory, harvest energy from a Kerr black hole by repeatedly sending matter into the ergosphere and extracting the energized fragments. This is the basis of speculative megastructures like the Penrose sphere, a hypothetical construct that surrounds a black hole and captures energy from the Penrose process. Pure science fiction, but grounded in real physics. The equations allow it. Whether engineering allows it is another question entirely. Now let us talk about how fast black holes spin. Observations of supermassive black holes, particularly those with active accretion disks and jets, suggest that many are spinning at close to the maximum rate allowed by general relativity. The spin parameter, usually denoted by the letter A, ranges from 0 for a non-rotating black hole to 1 for a maximally rotating black hole. A spin parameter of 1 means the black hole is rotating at the speed where the event horizon and the ergosphere meet at the poles. The black hole cannot spin faster than this because additional angular momentum would push the event horizon inward, causing it to disappear and exposing the singularity. This is called a naked singularity, and it is forbidden by the cosmic censorship conjecture. The conjecture, proposed by Roger Penrose in 1969, states that singularities must always be hidden behind event horizons. We have never observed a naked singularity. And if the cosmic censorship conjecture is correct, we never will. The universe, for reasons we do not fully understand, appears to enforce modesty. It hides its infinities. M87 star has been measured to have a spin parameter of approximately 0.9. It is spinning at 90% of the maximum possible rate. This means the ergosphere extends far from the event horizon. The frame dragging effect is extreme, and the jets, those beams of plasma shooting out at 99% the speed of light, are likely powered by the extraction of rotational energy from the black hole through magnetic fields threading the ergosphere. Sagittarius A star, by contrast, has a much lower spin. Estimates suggest a spin parameter of approximately 0.1. It is rotating slowly, almost lazily. Why the difference? We do not know. Perhaps Sagittarius A star has not accreted much matter recently. Perhaps it formed from a slower rotating progenitor. Perhaps it experienced a retrograde merger where an object fell into it from the opposite direction, reducing its spin. Black holes record their history in their spin, but we can only read that history if we can measure the spin. And measuring spin requires detailed observations of the accretion disk or gravitational wave signals from mergers. Let us now compare black holes to other structures in the universe. We have established their size, their mass, but how do they fit into the cosmic hierarchy? Start with atoms. The Bohr radius of a hydrogen atom is approximately 5.3 times 10 to the power of -11 meters. That is 0.053 nanometers. A single proton has a diameter of approximately 1.7 femtometers, 1.7 times 10 to the power of -15 meters. A stellar mass black hole's event horizon at 57 kilometers is approximately 3.3 times 10 to the power of 19 times larger than a proton. The Sun has a diameter of 1.392 million kilometers. A stellar mass black hole's event horizon is approximately 24,000 times smaller than the Sun. M87 star's event horizon at 38 billion kilometers is approximately 27 times larger than the Sun. TON 618's event horizon at 773 billion kilometers is approximately 555 times larger than the Sun. But even these numbers do not convey the true scale. Let us talk about density. Density is mass divided by volume. A stellar mass black hole with 10 solar masses and an event horizon diameter of 57 kilometers has a volume of approximately 9.7 times 10 to the power of 13 cubic meters. Its mass is approximately 1.989 times 10 to the power of 31 kilograms. Divide mass by volume and you get a density of approximately 2.05 times 10 to the power of 17 kilograms per cubic meter. That is 200 quadrillion kilograms per cubic meter. For comparison, the density of water is 1,000 kilograms per cubic meter. The density of lead is approximately 11,300 kilograms per cubic meter. The density of a white dwarf star is approximately 1 million kilograms per cubic meter. The density of a neutron star is approximately 4.0 times 10 to the power of 17 kilograms per cubic meter. A stellar mass black hole, averaged over the volume inside its event horizon, has a density comparable to a neutron star. But this is misleading. The mass is not spread throughout the volume. It is concentrated at the singularity, a point. The density at the singularity is infinite. The average density inside the event horizon is a fiction, a mathematical convenience. It tells us nothing about the reality of the singularity. Now consider a supermassive black hole, M87 star, with 6.5 billion solar masses and an event horizon diameter of 38 billion kilometers, has a volume of approximately 2.87 times 10 to the power of 31 cubic meters. Its mass is approximately 1.29 times 10 to the power of 39 kilograms. The average density inside the event horizon is approximately 4.5 times 10 to the power of 7 kilograms per cubic meter. 45 million kilograms per cubic meter. That is 45,000 times denser than water. It sounds dense, but it is actually less dense than a neutron star. Less dense than a white dwarf. Why? Because the volume increases as the cube of the radius, while the mass increases linearly. Larger black holes are less dense on average. TON 618, with its 66 billion solar masses, has an even lower average density, approximately 1.3 times 10 to the power of 6 kilograms per cubic meter. 1.3 million kilograms per cubic meter. Still incredibly dense by everyday standards. But if you could somehow survive inside the event horizon, if you could float in the space between the horizon and the singularity, you would not be compressed. Not immediately. The space is vast. The tidal forces at the horizon are weak. You would fall inward, always inward. But for a time, you would exist in a volume that is, by cosmic standards, almost empty. Let us talk about what we can see. Because black holes, despite being black, are among the brightest objects in the universe when they feed. Quasars, the most luminous objects known, powered by supermassive black holes accreting matter at rates of several solar masses per year. That is multiple suns' worth of gas falling into the black hole every year. The efficiency of conversion, approximately 10%, means that 10% of that mass is converted into energy. E equals mc squared, mass times the speed of light squared. One solar mass, if entirely converted to energy, yields approximately 1.8 times 10 to the power of 47 joules. 10% of that is 1.8 times 10 to the power of 46 joules. The Sun's total luminosity is approximately 3.8 times 10 to the power of 26 watts. 1 watt is 1 joule per second. If a black hole accretes 1 solar mass per year and converts 10% to energy, the luminosity is approximately 5.7 times 10 to the power of 38 watts. That is 1 trillion times more luminous than the Sun. 1 trillion. And many quasars are even brighter. The brightest quasars have luminosities exceeding 10 to the power of 40 watts. 10,000 trillion times the Sun's luminosity, from a region smaller than our solar system. And we can see these quasars from billions of light years away. The light from the most distant quasars has been traveling for over 13 billion years. It left those black holes when the universe was less than 1 billion years old. And it is still bright enough to detect with our telescopes. This tells us something profound. Supermassive black holes formed early, very early, within the first billion years after the Big Bang. We do not fully understand how. Growing a billion solar mass black hole requires either an extremely massive seed, perhaps from the direct collapse of a primordial gas cloud, or an exceptionally high accretion rate sustained over hundreds of millions of years. Both scenarios push the limits of our models, and yet the observations are clear. These monsters existed when the universe was young. They were already feeding, already dominating their host galaxies. Let us talk about those host galaxies, because there is a relationship between the mass of a supermassive black hole and the properties of the galaxy surrounding it. This relationship is called the M-sigma relation. M is the black hole mass. Sigma is the velocity dispersion of stars in the galactic bulge, the measurement of how fast stars are moving, on average, in the central region of the galaxy. Observations show a tight correlation. Galaxies with faster-moving stars in their centers have more massive black holes. The relationship is roughly linear on a logarithmic scale. A galaxy with a velocity dispersion of 200 kilometers per second typically hosts a black hole with a mass of approximately 100 million solar masses. Double the velocity dispersion to 400 kilometers per second, and the black hole mass increases to approximately 1 billion solar masses. This correlation holds across 6 orders of magnitude, from dwarf galaxies with black holes of a few 100,000 solar masses to giant ellipticals with black holes exceeding 10 billion solar masses. But why does this correlation exist? The black hole is tiny compared to the galaxy. Sagittarius A star, at 4 million solar masses, contains only 0.1% of the Milky Way's total stellar mass. It is a rounding error. And yet, the correlation is real, tight, consistent. The leading explanation is coevolution. The black hole and the galaxy grow together. When gas falls toward the galactic center, some of it feeds the black hole and some of it forms stars. The black hole's accretion disk and jets pump energy into the surrounding gas, heating it, sometimes even expelling it from the galaxy entirely. This feedback regulates star formation. A more massive black hole produces more energetic feedback, which can suppress star formation more effectively. Over billions of years, the black hole and the galaxy reach an equilibrium. The black hole grows until its feedback prevents further growth. The galaxy grows until the black hole's feedback limits additional star formation. They balance each other, a cosmic symbiosis, or perhaps a cosmic predator-prey relationship. The black hole feeds on the galaxy, and the galaxy, in turn, is shaped by the black hole's appetite. This has implications for the question of scale, because it means that black holes are not isolated objects. They are embedded in galaxies. They influence their environments. They sculpt the universe. Without supermassive black holes, galaxies would look different. Star formation would proceed differently. The intergalactic medium would have a different temperature and density. The universe's large-scale structure might be different. Black holes are not passive. They are active participants in cosmic evolution. And they are everywhere. Every large galaxy we observe has a supermassive black hole at its center. This is not a coincidence. It is a rule, a law of galactic structure, and we do not fully understand why. Let us now turn to what happens when black holes collide. We have mentioned gravitational wave detections. But let us explore the mechanics. When two black holes orbit each other, they radiate gravitational waves. These waves carry energy away from the system. As energy is lost, the orbit decays. The black holes spiral closer together. The orbital period decreases. They move faster. The gravitational waves become stronger. The energy loss accelerates. The process is a runaway, exponential. In the final seconds before merger, the black holes are orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light, radiating gravitational waves with a power output that briefly exceeds the combined light output of every star in the observable universe. For a fraction of a second, a merging black hole binary is the most powerful event in the universe, more energetic than a supernova, more energetic than a gamma-ray burst. The only difference is that the energy is emitted not as light, but as gravitational waves, ripples in space-time, invisible to telescopes, detectable only by interferometers measuring changes in length smaller than a proton. When the black holes merge, the event horizons touch. They merge. Topology changes. Two disconnected surfaces become one. The geometry of space-time reorganizes itself. The final black hole is distorted, not spherical. It vibrates, rings, the ring down. The oscillations emit gravitational waves at frequencies determined by the final black hole's mass and spin. And then, within milliseconds, the oscillations decay. The black hole settles into a stable Kerr configuration. A spinning black hole. Stationary. Silent. The merger is complete. And somewhere in the universe, a new black hole exists, more massive than either of its progenitors, carrying the combined mass minus the energy radiated as gravitational waves. Typically, a few percent of the total mass is lost to gravitational radiation. For a merger of two 30 solar mass black holes, producing a final black hole of approximately 60 solar masses, the energy radiated is equivalent to 3 solar masses, 3 suns. Erased, converted entirely into gravitational wave energy. E equals mc squared, 3 times 2 times 10 to the power of 30 kilograms times 9 times 10 to the power of 16 meters squared per second squared. Approximately 5.4 times 10 to the power of 47 joules, released in less than 1 second. This is the most efficient energy extraction process we have ever observed in nature. And these mergers are common. LIGO and Virgo detect them regularly, approximately once per week on average when the detectors are operating. Each detection tells us about the population of black holes in the universe, their masses, their spins, their merger rates. We now know that stellar mass black holes exist in the range from approximately 5 solar masses to over 100 solar masses. We know that binary black hole systems are relatively common, and we know that black holes can merge multiple times over cosmic history. A black hole that forms from a stellar collapse can merge with another black hole, forming a larger black hole, which can then merge with another black hole, and so on. This hierarchical merging is thought to be one mechanism by which supermassive black holes grow, starting from stellar mass seeds and growing through successive mergers over billions of years. But there is a gap, a mystery, between the most massive stellar mass black holes detected by LIGO, around 100 solar masses, and the least massive supermassive black holes, around 100,000 solar masses. There is a range where we have detected almost nothing. This is called the intermediate mass black hole gap. Black holes with masses between 100 and 100,000 solar masses should exist. Theory predicts them, but observations are sparse. We have a few candidates. Objects observed in globular clusters, or the centers of dwarf galaxies, with masses estimated in the thousands or tens of thousands of solar masses. But the data is uncertain, ambiguous. These objects are difficult to detect because they are not massive enough to dominate their environments like supermassive black holes. And they are not common enough to be frequently detected by gravitational wave observatories like LIGO. Filling this gap is one of the major goals of next-generation gravitational wave detectors. LISA, the Laser Interferometer Space Antenna, a space-based detector scheduled for launch in the 2030s. LISA will be sensitive to lower-frequency gravitational waves than LIGO, waves with periods of minutes to hours rather than milliseconds. These are the waves emitted by merging black holes in the intermediate mass range and by supermassive black hole mergers. LISA will open a new window. It will detect the mergers of supermassive black holes at cosmological distances. It will, for the first time, allow us to observe the growth of these monsters in real time. Imagine that. A supermassive black hole merger. Two galaxies collide. Their central black holes, each with masses of billions of solar masses, spiral toward each other over millions of years. The galaxies merge, the stars intermingle, the gas clouds collide and ignite with new star formation, and at the center, the two black holes orbit each other, closer and closer, emitting gravitational waves. LISA detects the signal years before the merger. We watch as the orbital frequency increases. We measure the masses, the spins. We predict when the merger will occur. And then, at the moment of coalescence, the two event horizons merge. The combined black hole, containing the mass of tens of billions of suns, rings like a bell. The gravitational waves wash over us. LISA records the ringdown, and somewhere, billions of light-years away, a new supermassive black hole has been born. The most massive object in its galaxy, the gravitational anchor of an entire cosmic structure. But let us return to the immediate, the local, the personal. Let us talk about what a black hole would look like if you could see one up close, not from billions of light years away, not as a mathematical abstraction, but with your eyes, human eyes. Standing on a planet orbiting a star near a black hole, what would you see? First, you would not see the black hole itself. The event horizon absorbs all light that crosses it. It is perfectly black. But you would see its silhouette, a dark circle against the background of stars. And around that circle, you would see something extraordinary, an accretion disk. If the black hole is feeding, if there is matter spiraling inward, that matter glows. The inner edge of the disk, closest to the event horizon, shines in X-rays. Too high energy for human eyes, but the outer regions glow in visible light. Reds, oranges, yellows, blues at the hottest points. And the disk would be distorted. Gravitational lensing. Light from the far side of the disk curves around the black hole. You see the top of the disk. You see the bottom of the disk. And you see the back of the disk warped around the edges, visible as a glowing arc above and below the black hole's silhouette. The entire structure looks like a glowing ring, a halo, with a dark center. This is what the Event Horizon Telescope captured in April 2017 when it imaged M87 star, a blurry orange ring. The photon ring. Light from the accretion disk bent by the black hole's gravity into a circular pattern. The dark center is not the event horizon. It is larger. It is the black hole's shadow. The region from which no light can escape to reach us. The shadow is approximately 2.6 times larger than the event horizon. For M87 star, the shadow has a diameter of approximately 99 billion kilometers. The event horizon itself, hidden within the shadow, is 38 billion kilometers across. But we cannot see the event horizon, we see only its shadow, the absence of light, and if you were close enough to see this, you would experience time dilation, severe time dilation. Time flows more slowly in strong gravitational fields. This is not science fiction. This is experimentally verified. GPS satellites in orbit around Earth experience less gravity than we do on the surface, and their clocks run faster. Only by microseconds per day, but enough that GPS navigation would fail if the system did not correct for relativistic effects. Near a black hole, the time dilation is extreme, measurable, deadly. Imagine you are in a spacecraft hovering just outside the event horizon of M87 star. Your engines are firing constantly, fighting the gravitational pull, keeping you stationary relative to the distant stars. You look at your watch. 1 second passes, but to an observer far from the black hole, watching you through a telescope, your clock appears to be running slowly, very slowly. Time dilation follows a mathematical relationship. The closer you get to the event horizon, the slower your clock runs relative to distant observers. At a distance of twice the Schwarzschild radius, your clock runs at approximately 71% of the normal rate. At 1.5 times the Schwarzschild radius, 57%. At 1.1 times the Schwarzschild radius, 31%. And as you approach the event horizon itself, your clock slows asymptotically. It approaches zero. At the event horizon, from the perspective of a distant observer, your clock stops, you freeze. Time, for you, relative to the outside universe, ceases to progress. But from your perspective, inside the spacecraft hovering near the event horizon, everything feels normal. Your watch ticks at 1 second per second. Your heart beats at its normal rate. Your thoughts progress normally. You do not feel time slowing. Because time, for you, is always normal. It is only when you compare your clock to clocks farther from the black hole that the difference becomes apparent. You look out the window. You see the universe. And the universe is running fast. Stars evolve and fast forward. Galaxies rotate at accelerated speeds. If you hovered near the event horizon for what felt like 1 hour, and then accelerated away and returned to a safe distance, you might find that decades have passed in the outside universe. Your friends are older, or dead. Civilizations have risen and fallen. The universe has moved on without you. You have traveled into the future. Not through faster-than-light travel, not through wormholes, but through the curvature of space-time, through gravity. This is real. This is general relativity. And it has been tested. In 1971, physicist Joseph Huffelli and astronomer Richard Keating flew atomic clocks around the world on commercial airliners. When they returned, they compared the clocks to identical clocks that had remained on the ground. The airborne clocks had experienced less gravitational time dilation because they were at higher altitude, but they also experienced kinetic time dilation because they were moving. The net result, predicted by relativity, was that the eastward flying clocks lost 59 nanoseconds, while the westward flying clocks gained 273 nanoseconds. The experiment confirmed the predictions with an experimental error. Time dilation is real. Gravity dilates time. And near a black hole, the effect is not nanoseconds. It is seconds, minutes, hours, years. Now let us talk about what happens to light near a black hole. Gravitational redshift. Light climbing out of a gravitational well loses energy. Its wavelength stretches. Blue light becomes red. Red becomes infrared. Infrared becomes radio waves. This is not the Doppler effect. It is not caused by motion, it is caused by gravity. Light emitted near the event horizon of a black hole must climb an enormous gravitational potential to reach a distant observer. As it climbs, it loses energy. The frequency decreases. If you were hovering near the event horizon with a flashlight emitting blue light, an observer far from the black hole would see your flashlight as red or infrared, or maybe not at all. If the gravitational redshift is so severe that the light shifts into wavelengths their equipment cannot detect, and if you fell toward the event horizon, emitting light continuously, the observer would see your light redshift progressively, blue to red to infrared to radio, until finally, as you crossed the horizon, the light would redshift to infinite wavelength, zero energy. It would disappear. Not because you stopped emitting, but because the light could no longer escape. It would be trapped just inside the horizon, orbiting the singularity, never reaching the outside universe. And here is another effect: gravitational lensing. Light bends in a gravitational field. The stronger the gravity, the more severe the bending. A black hole bends light to extreme degrees. If you looked at a black hole with a bright star directly behind it, you would not see one star. You would see multiple images of the star. Light from the star approaches the black hole from different angles. Some light passes above the black hole, some below, some to the left, some to the right. All of it bends. And depending on the alignment, you might see the star as a ring. An Einstein ring, a perfect circle of light surrounding the black hole's shadow. This effect has been observed for massive galaxy clusters lensing background galaxies. But for a black hole, the lensing is more extreme, more distorted. The photon ring around M87 star is, in part, a result of this extreme lensing. Light from the accretion disk bends around the black hole in complex trajectories, creating the glowing halo we observe. Let us talk about specific black holes. Real objects, observed, measured, cataloged. We have already discussed Sagittarius A star, M87 star, and TON 618. But there are others. Cygnus X1, the first black hole candidate ever identified, discovered in 1964 during a rocket flight carrying Geiger counters above Earth's atmosphere. The detectors recorded X-rays from a source in the constellation Cygnus. Follow-up observations identified a blue supergiant star, HDE 226868, orbiting an invisible companion every 5.6 days. The orbital motion revealed the companion's mass, approximately 15 solar masses. Too massive to be a neutron star, it had to be a black hole. For decades, this was debated. Some astronomers proposed alternative explanations. But in 2011, observations confirmed it. Cygnus X1 is a black hole. 15 solar masses. Event horizon diameter approximately 88 kilometers. And it is feeding. Gas from the blue supergiant flows toward the black hole, forming an accretion disk that emits X-rays detectable across 6,000 light-years of space. GRO J1655-40. A black hole in a binary system with a companion star. The black hole has a mass of approximately 6.3 solar masses. Unremarkable in size, but remarkable in behavior. This system produces quasi-periodic oscillations, regular pulses of X-rays with frequencies around 450 Hz, 450 pulses per second. These oscillations are thought to originate from the inner edge of the accretion disk, where matter orbits the black hole at significant fractions of the speed of light. The frequency of the oscillations corresponds to the orbital period at the innermost stable circular orbit, the ISCO, the last stable orbit before matter plunges into the event horizon. For a non-rotating black hole, the ISCO is located at 3 times the Schwarzschild radius. For a maximally rotating Kerr black hole, it is located at the Schwarzschild radius itself. The frequency of quasi-periodic oscillations allows us to measure the black hole's spin. And for GRO J1655-40, the observation suggests a high spin. The black hole is rotating rapidly, nearly maximal. And then there is NGC 1277, a galaxy approximately 250 million light-years away. In March 2011, astronomers observed a sudden brightening in the galactic nucleus. A tidal disruption event. A star wandered too close to the supermassive black hole at the galaxy's center. The tidal forces, the difference in gravitational pull between the near and far sides of the star, exceeded the star's self-gravity. The star was torn apart, shredded. The debris formed an accretion disk around the black hole. The disk heated up. It glowed, emitted X-rays. We watched for months as the black hole consumed the remains of the star. The luminosity peaked, then slowly declined as the supply of infalling matter decreased. The black hole at the center of NGC 1277 has an estimated mass of approximately 1 million solar masses, modest by supermassive standards, but large enough to destroy a star that ventured too close. Tidal disruption events are rare. They occur in a given galaxy approximately once every 10,000 to 100,000 years. But with modern surveys monitoring millions of galaxies, we detect several per year. Each one provides a glimpse of a supermassive black hole waking up, feeding, announcing its presence through violence. Let us talk about what black holes do to galaxies. We have mentioned feedback. Jets and radiation from accreting black holes heat the surrounding gas, sometimes expelling it from the galaxy entirely. This process is thought to regulate star formation. But there is another effect: gravitational interactions. When a galaxy merges with another galaxy, the 2 central black holes eventually sink to the center of the merged system. They orbit each other, and as they orbit, they interact gravitationally with nearby stars. Stars passing close to the binary black hole system can be flung outward at high velocities. Ejected from the galaxy entirely, these are called hypervelocity stars. Stars moving at speeds exceeding the galaxy's escape velocity. We have detected several hypervelocity stars in the Milky Way. Stars moving at over 500 kilometers per second, fast enough to escape the galaxy's gravitational pull. The leading explanation for their existence is a close encounter with Sagittarius A star, or a binary black hole system in the galactic center. A star approaches. It swings around one of the black holes. The gravitational slingshot accelerates it to extreme velocities, and the star is ejected, launched into intergalactic space, forever separated from its birthplace. Black holes also create gravitational wave backgrounds. Individual black hole mergers produce short bursts of gravitational waves, chirps lasting seconds or less. But the universe contains billions of merging black hole binaries. At any given moment, countless binaries are spiraling together, emitting gravitational waves. The combined effect is a stochastic background, a low-level hum of gravitational radiation filling the universe. Pulsar timing arrays, networks of precisely monitored millisecond pulsars, are beginning to detect this background. In June 2023, multiple collaborations announced evidence for a gravitational wave background at nanohertz frequencies, waves with periods of years to decades. The signal is consistent with predictions for the background produced by supermassive black hole binaries, millions of pairs of billion solar mass black holes orbiting each other in galaxies across the universe, creating a cosmic chorus of gravitational waves. We are beginning to hear it, a faint signal, but real. And as observations improve, we will map this background. We will learn about the population of supermassive black hole binaries, their masses, their merger rates, the history of galaxy mergers across cosmic time. Now let us confront what black holes tell us about the fabric of reality itself. Because a black hole is not just a massive object, it is a laboratory, a testing ground for physics at its most extreme. Inside a black hole, at the singularity, our equations break down. General relativity predicts infinite density, infinite curvature. Infinities appear in the math. And in physics, infinity is a red flag. It signals that the theory is incomplete, that something is missing. Near the singularity, quantum effects must become important. Space and time at the Planck scale, approximately 10 to the power of -35 meters, the scale at which quantum gravity should dominate. But we do not have a working theory of quantum gravity, we have attempts. String theory, loop quantum gravity, various approaches to unifying general relativity and quantum mechanics. But none have been experimentally confirmed. The singularity remains a mystery, a place where the known laws of physics do not apply. And this brings us to the holographic principle, one of the strangest ideas in modern physics. The principle states that all the information contained within a volume of space can be encoded on the boundary of that space. Like a hologram, a two-dimensional surface containing information about a three-dimensional object. This idea emerged from studying black holes. Jacob Bekenstein in 1973 proposed that black holes have entropy, a measure of disorder or information, and that this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. The surface area, in square Planck units. Each Planck area, approximately 10 to the power of -70 meters squared, corresponds to 1 bit of information. The entropy of a black hole, its information content, is given by the area of its event horizon divided by 4 times the Planck area. For a stellar mass black hole with 10 solar masses, the entropy is approximately 10 to the power of 77 bits. For M87 star, it is approximately 10 to the power of 91 bits. These are staggeringly large numbers, but they are finite, and they scale with area, not volume. This implies something profound. If the information content of a black hole is determined by its surface area, then perhaps the same is true for any region of space. Perhaps the three-dimensional universe we perceive is actually a projection. A hologram encoded on a two-dimensional boundary at the edge of space. This is the holographic principle. And while it sounds like science fiction, it is taken seriously by theoretical physicists. It arises naturally in string theory and in attempts to understand quantum gravity. If the holographic principle is correct, then reality is not what it seems. The 3 dimensions of space we experience might be emergent, derived from a more fundamental 2-dimensional structure. And black holes, with their event horizons and entropy, are the key to understanding this. Let us talk about the firewall paradox, another deep puzzle at the intersection of black holes and quantum mechanics. Hawking radiation, the quantum process by which black holes evaporate, creates entangled particles. One particle falls into the black hole, the other escapes. They are quantum mechanically correlated, entangled, but as the black hole evaporates, eventually the escaping radiation must carry away all the information that fell into the black hole. To preserve information, the late-time radiation must be entangled not just with the radiation emitted earlier, but also with the matter inside the black hole. But quantum mechanics forbids this. A particle cannot be maximally entangled with two different systems. This is called the monogamy of entanglement. Something has to give. Either information is lost, violating quantum mechanics, or the equivalence principle, the idea that an observer crossing the event horizon should experience nothing unusual, must be violated. In 2012, physicists Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully proposed a radical solution: the firewall. They argued that the event horizon must be replaced by a wall of high-energy particles, a firewall that incinerates anything that crosses it. This preserves information in quantum mechanics, but violates the equivalence principle. It means that falling into a black hole would not be a smooth transition. You would burn instantly, vaporized at the horizon. And yet, general relativity insists there should be nothing special at the horizon. The paradox remains unresolved. Different physicists favor different solutions. But the firewall paradox reveals how little we understand about the interplay between gravity and quantum mechanics. Black holes are not just objects to be observed and measured. They are puzzles, challenges to our deepest theories. Now let us talk about primordial black holes, a hypothetical class of black holes that might have formed in the early universe. Not from collapsing stars, but from density fluctuations in the primordial plasma. In the first fraction of a second after the Big Bang, the universe was extremely dense and hot. Small regions that were slightly denser than average could have collapsed directly into black holes. These primordial black holes could have a wide range of masses, from as small as the Planck mass, approximately 10 to the power of -8 kilograms, to thousands of solar masses. Smaller primordial black holes would have evaporated already through Hawking radiation. Any black hole with an initial mass less than approximately 10 to the power of 12 kilograms would have evaporated completely by now after 13.8 billion years. But larger primordial black holes, if they exist, would still be around. And they are candidates for dark matter, the mysterious substance that makes up approximately 27% of the universe's mass energy content but does not emit, absorb, or reflect light. If primordial black holes with masses in the range of tens of solar masses were abundant in the early universe, they could account for dark matter. They would cluster gravitationally. They would produce the gravitational effects we attribute to dark matter. And they would be invisible, perfectly black. We have searched for primordial black holes through gravitational lensing. If a primordial black hole passes between us and a distant star, it would briefly magnify the star's light. Microlensing. Surveys have placed constraints on the abundance of primordial black holes in certain mass ranges. The constraints are tight. Primordial black holes with masses between 10 to the power of 17 and 10 to the power of 26 kilograms cannot make up a significant fraction of dark matter. There are not enough of them. But other mass ranges remain open. The search continues, and if primordial black holes exist, they would be fossils from the Big Bang, relics of the earliest moments of cosmic history. Studying them would reveal the conditions in the primordial universe, the density fluctuations, the physics at energies far beyond what we can achieve in particle accelerators. Let us talk about what black holes mean for the fate of the universe. The universe is expanding. And the expansion is accelerating, driven by dark energy. If this acceleration continues indefinitely, galaxies will drift apart. Galaxy clusters will dissolve. Eventually, in trillions of years, galaxies will be isolated, alone in an expanding void. Star formation will cease as gas is exhausted. Stars will age and die. The last stars, the smallest red dwarfs, will burn for trillions of years. But eventually, they too will fade. The universe will enter the degenerate era, a time when the only sources of light are white dwarfs, neutron stars, and black holes. White dwarfs will cool. Over tens of trillions of years, they will radiate away their heat, becoming black dwarfs. Cold, dark cinders. Neutron stars will cool similarly, and black holes will remain, patient, unchanging, fed by the occasional piece of matter that falls too close. But even black holes are not eternal. Hawking radiation ensures that black holes evaporate, slowly, over time scales so long they defy comprehension. A solar mass black hole will evaporate in approximately 10 to the power of 67 years. A supermassive black hole with 1 billion solar masses will take approximately 10 to the power of 99 years. The current age of the universe is approximately 10 to the power of 10 years. We would need to wait approximately 10 to the power of 89 times longer than the universe has currently existed before 1 billion solar mass black hole evaporated. These timescales are absurd, but they are finite. In the black hole era, from approximately 10 to the power of 40 years to 10 to the power of 100 years after the Big Bang, black holes will be the dominant structures, slowly evaporating. Eventually, they will all be gone. The universe will enter the dark era, a time with no stars, no galaxies, no black holes. Only photons, neutrinos, and perhaps some exotic particles. The universe will be cold, dark, empty, expanding forever, approaching absolute zero asymptotically, but never quite reaching it. This is the heat death of the universe, the final equilibrium state. Maximum entropy. No gradients, no structure, no complexity, no life. The universe will continue to exist, but nothing will happen. No events, no change. Just an endless expanding void, filled with dilute radiation growing ever colder as space stretches. This is the fate predicted by our current understanding of cosmology. Dark energy dominates, the expansion accelerates, structure dissolves, entropy increases. And eventually the universe reaches a state of maximum disorder from which no recovery is possible. But black holes play a critical role in this fate. They are the final compact objects, the last reservoirs of organized matter and energy. They are the slowest to succumb to entropy. They resist decay for eons longer than any star or planet. In a sense, black holes are the universe's final stand against heat death, the last defiance. But even they lose. Hawking radiation, that quantum whisper from the event horizon, ensures that every black hole will eventually evaporate, will return its mass energy to the void. And when the last black hole evaporates, in the unimaginably distant future, the universe will have won. Or lost, depending on your perspective. Entropy will be maximized. Order will be gone. And nothing interesting will ever happen again. This is speculative, of course. Our understanding of dark energy is incomplete. We do not know if the acceleration will continue forever. Perhaps dark energy will decay. Perhaps the expansion will slow. Perhaps the universe will recollapse in a big crunch, with all matter and energy converging back to a singularity. Or perhaps something stranger will happen. Vacuum decay, a phase transition in the quantum fields that permeate space. If the vacuum we live in is metastable, a false vacuum, then it could decay to a lower energy true vacuum. The decay would propagate as a bubble expanding at the speed of light. Inside the bubble, the laws of physics would be different. Particle masses would change, atoms would disintegrate, everything would be destroyed. And we would have no warning. The bubble wall would hit us at the speed of light. We would not see it coming. One moment, the universe exists. The next, it is erased, replaced by a new vacuum, a new physics, incompatible with the structures and life that existed in the old vacuum. Black holes also tell us something about causality, about the arrow of time. Inside the event horizon, the roles of space and time swap. In normal space-time, you can move freely in space but are forced to move forward in time. You can go left or right, forward or backward, up or down. But you cannot go backward in time. Time has one direction, forward, always forward. Inside a black hole's event horizon, this changes. The radial direction, the direction toward the singularity, becomes time-like. You are forced to move toward the singularity, just as you are forced to move forward in time outside the horizon. It becomes as inevitable as aging, as unavoidable as tomorrow. Meanwhile, time itself becomes space-like in a sense. The mathematics becomes strange, difficult to interpret, but the implication is clear. Inside the event horizon, all futures lead to the singularity. There is no escape, not because you lack the means, but because the structure of space-time itself forbids it. This reveals something profound about the nature of reality. Space-time is not a fixed stage on which events play out. It is dynamic, flexible, curved by mass and energy. And in extreme conditions, it can be curved so severely that the familiar concepts of space and time break down. Inside a black hole, causality itself is warped. The future is constrained, predetermined, not by fate or destiny, but by geometry, by the curvature of the manifold on which existence is embedded. Let us talk about what we still do not know. Because for all our observations and equations, black holes remain mysterious. We do not know what happens at the singularity. General relativity predicts infinite density and infinite curvature. But infinity is not physical. It is a signal that the theory fails. Quantum gravity, whatever form it takes, must resolve the singularity. Perhaps the singularity is replaced by a Planck-scale structure, a tiny, incredibly dense core where quantum effects dominate. Perhaps space-time itself is quantized at the smallest scales, discrete rather than continuous, pixels rather than a smooth sheet. String theory suggests that singularities might be avoided if fundamental particles are not points but tiny vibrating strings, or higher dimensional objects called brains. Loop quantum gravity proposes that space-time has a granular structure at the Planck scale. But we have no experimental evidence for any of this. The singularity remains hidden. Protected by the event horizon, we cannot observe it directly. We can only theorize. We do not know if naked singularities can exist, singularities without event horizons. General relativity allows solutions where rotating black holes spin so fast that the event horizon disappears, exposing the singularity to the outside universe. But the cosmic censorship conjecture forbids this. And observations suggest the conjecture is correct. We have never detected a naked singularity, but we cannot prove they are impossible. Perhaps there are exotic mechanisms that could create one. Perhaps in the early universe, under extreme conditions, naked singularities formed. Or perhaps the conjecture is wrong. If a naked singularity exists, it would be a window into the singularity, a place where we could observe the breakdown of space-time, where we could test our theories of quantum gravity. But it would also be a violation of causality, a place where the predictability of physics breaks down, where anything could happen. This is why most physicists believe naked singularities cannot exist. The universe protects itself from such pathologies. We do not fully understand how supermassive black holes grow. We know they exist in the early universe, less than 1 billion years after the Big Bang. But building a billion solar mass black hole in that time is challenging. Accretion is limited by the Eddington limit, the maximum rate at which a black hole can accrete matter before radiation pressure from the heated accretion disk pushes the infalling matter away. For a solar mass black hole, the Eddington limited accretion rate is approximately 10 to the power of -8 solar masses per year. To grow from a stellar mass seed to 1 billion solar masses in 1 billion years, a black hole would need to accrete at rates far exceeding the Eddington limit, or it would need to start from a much more massive seed, perhaps a direct collapse black hole. A massive cloud of gas collapsing into a black hole without forming a star first. These could have masses of thousands or tens of thousands of solar masses from birth. Or perhaps supermassive black holes form through mergers, smaller black holes colliding and combining repeatedly. Or perhaps there are mechanisms we have not yet discovered, exotic accretion processes operating in the extreme conditions of the early universe. We do not know if black holes have hair, quantum hair. The no-hair theorem states that black holes are characterized entirely by mass, spin, and charge, no other properties. But quantum mechanics suggests that additional information might be encoded somehow, perhaps in subtle correlations in the Hawking radiation, perhaps in quantum states at the event horizon. Some physicists have proposed that black holes could have soft hair, low-energy quantum excitations at the horizon that carry information without violating the no-hair theorem. Others have proposed that black holes might have discrete quantum states, that there are many different black holes with the same mass, spin, and charge, distinguished by internal quantum numbers. This would resolve the information paradox. The information would not be lost, it would be preserved in the quantum state of the black hole. But we have no way to test this. Not yet. Let us return to observations, to what we can measure. In 2020, astronomers announced the discovery of an intermediate mass black hole candidate. A black hole with a mass of approximately 850 solar masses. It was detected through gravitational waves. The signal, designated GW190521, was produced by the merger of two black holes, with masses of approximately 85 and 66 solar masses. The final black hole, after the merger, had a mass of approximately 142 solar masses. But the interesting part is one of the progenitors. 85 solar masses, this is in the mass gap. The range where stellar evolution theory predicts black holes should not exist. Stars massive enough to produce black holes above approximately 50 solar masses should undergo pair instability supernovae, a catastrophic explosion that completely disrupts the star, leaving no remnant. And yet, the 85 solar mass black hole existed. It merged with another black hole. Where did it come from? The leading explanation is hierarchical merging. It was itself the product of an earlier merger. Two smaller black holes merged, producing a black hole in the mass gap. This black hole then participated in a second merger, the one we detected. This tells us that black hole mergers can happen in clusters, dense stellar environments where black holes sink to the center and merge repeatedly, each generation producing more massive black holes. In 2023, astronomers using the James Webb Space Telescope detected the most distant supermassive black hole known, a quasar at a redshift of 10.1. This corresponds to a time when the universe was only 450 million years old. 450 million years. The black hole has a mass of approximately 10 million solar masses. How did it grow so large so quickly? We do not know. This is one of the major puzzles in astrophysics. Supermassive black holes in the very early universe challenge our models of structure formation. They should not exist yet, but they do, and they are not alone. JWST is finding more massive black holes at high redshift than expected. The universe was assembling structure faster than we thought. Black holes were growing faster. Galaxies were forming earlier. This forces us to revise our models, to reconsider the physics of the early universe. Now let us bring this back to you, to scale, to the question of how small we are. Because that is the point of this journey. You are approximately 1.7 meters tall. Your body contains approximately 7 times 10 to the power of 27 atoms. Each atom has a diameter of approximately 1 angstrom, 10 to the power of -10 meters. You are large compared to atoms, but small compared to planets. Earth has a diameter of approximately 12,742 kilometers. You are approximately 7.5 million times smaller than Earth. The Sun is approximately 818,000 times larger than you by linear dimension. Sagittarius A**'s event horizon, at 22 million kilometers diameter, is approximately 13 million times larger than you. M87's event horizon is approximately 2.2 billion times larger. TON 618 is approximately 455 billion times larger. These numbers are not hypothetical. These are real objects, measured, confirmed, existing right now in the universe. And you are so small compared to them that you would not register. You are less than a quantum fluctuation in their gravitational field. But let us also consider mass. You have a mass of approximately 70 kilograms. Sagittarius A* has a mass of approximately 8 times 10 to the power of 36 kilograms. You are approximately 1.1 times 10 to the power of -35 of its mass. That is a decimal point, followed by 34 zeros and then a 1. You could add 1 trillion copies of yourself to Sagittarius A* and it would not notice. The gravitational field would not change measurably. The event horizon would not grow detectably. You would be noise. Statistical error. Irrelevant. And for TON 618, with its 66 billion solar masses, you are approximately 8 times 10 to the power of -38 of its mass. These numbers are so small they cease to have meaning. You cannot visualize them. You cannot relate to them. You are so insignificant compared to these objects that language fails to capture the disparity. And yet, you exist. You are conscious. You can think about these objects. You can comprehend, at least mathematically, their scale. A black hole does not think. It does not wonder. It does not create art or music or science. It simply is. A structure in space-time, a solution to Einstein's equations. Deterministic, predictable, inevitable. You are complex, temporary, fragile. Your existence requires a precise set of conditions. A stable planet, a star that does not flare too violently, a galaxy that does not suffer too many supernova explosions nearby, an atmosphere, liquid water, organic chemistry, billions of years of evolution. You are the product of countless accidents, coincidences, contingencies. And you exist in a universe dominated by structures that could erase you without noticing. Let us consider what it means to fall into a black hole. Not abstractly, not mathematically, but experientially. You approach the event horizon. If the black hole is stellar mass, you are already dead, spaghettified thousands of kilometers away. But if it is supermassive, you cross. The moment passes without sensation. No barrier, no wall. Nothing changes visibly, but everything has changed. Behind you, the universe continues. Time flows forward. Stars evolve, civilizations rise and fall. But you cannot return. You cannot send a signal. You cannot influence anything outside. You are severed from causality, from the timeline of the cosmos. You fall. Inward. Always inward. Hours pass. Maybe days. The tidal forces remain weak. You are still alive, still conscious, but you know what is coming. Ahead of you, invisible in the darkness, the singularity waits. And as you approach, the tidal gradient steepens. Your feet accelerate faster than your head. The stretching begins, gentle at first, then severe. Your bones crack, your tissues tear, your cells rupture, and then your molecules, your atoms, the electromagnetic forces holding matter together, scream under the strain. And finally, they fail. You dissolve, not into pieces, into constituent particles, a stream of quarks and electrons spiraling into the singularity. And then, at the singularity itself, space-time curvature becomes infinite. The equations predict that you are compressed to zero volume, infinite density. But this cannot be physical. Something else must happen, something quantum, something we do not understand. You reach the place where physics breaks, where our knowledge ends. And whatever happens there, no information about it can ever escape. The universe will never know. You are deleted, erased from the ledger of existence. Not just killed, fundamentally removed from reality. This is the ultimate isolation, the ultimate insignificance. You are not just small compared to the black hole, you are erasable. Forgettable, a temporary pattern in the quantum foam that existed briefly and then vanished. The black hole does not remember you. It gains a negligible amount of mass. Its event horizon expands by a distance smaller than a proton. And that is all. You are gone, and the universe continues. Indifferent. Now consider that there are millions of stellar mass black holes in our galaxy alone. Millions. And 400 billion galaxies in the observable universe. Each with its own population of black holes. Each with a supermassive black hole at its center. The universe is filled with these structures, gravitational traps, regions of space-time from which there is no escape, and we exist on a tiny planet orbiting a mundane star. In a quiet region of one galaxy among hundreds of billions, we are surrounded. Everywhere you look, in every direction, billions of light years away, black holes exist. Feeding, growing, merging, dominating the gravitational architecture of the universe. And we are here. Fragile biological organisms clinging to a rock. Thinking, wondering, trying to understand. Let us talk about the sheer number. Astronomers estimate there are approximately 100 million stellar mass black holes in the Milky Way. 100 million. Most are invisible, quiet, not accreting matter, just wandering through space. Gravitational ghosts, each one a collapsed star, a monument to a violent death. And these are just in our galaxy. Multiply by 400 billion galaxies. The number becomes approximately 4 times 10 to the power of 19 stellar mass black holes. In the observable universe, 40 quintillion. Each one capable of destroying anything that comes too close. Each one a trap, a snare in the fabric of space-time. And that is just stellar mass black holes. Add the supermassive black holes, 1 per large galaxy, approximately 2 trillion in the observable universe, with masses ranging from millions to tens of billions of solar masses. The total mass contained in black holes is staggering, comparable to the mass in all the stars in the universe. Black holes are not rare. They are not exotic oddities. They are fundamental components of cosmic structure, and they are everywhere. Consider the fate of stars. Most stars will never become black holes. They are too small. They will end as white dwarfs or neutron stars. But the most massive stars, those born with more than 20 solar masses, are doomed. They burn fast, they die young, and they collapse into black holes. In the Milky Way, a star massive enough to produce a black hole is born approximately once every 1,000 years. Over the 10 billion year history of our galaxy, that is approximately 10 million black holes produced. Many have merged. Some have been ejected from the galaxy through gravitational interactions, but millions remain, and they will persist. Long after the last star fades, long after the universe enters the degenerate era, black holes will remain, patient, unchanging, waiting. Here is another way to think about scale. Light takes approximately 1.3 seconds to travel from the Moon to Earth. It takes 8 minutes and 20 seconds to travel from the Sun to Earth. It takes 4.24 years to reach the nearest star. It takes 26,000 years to travel from the galactic center to Earth. Every photon you see from Sagittarius A star, if we could see photons from the event horizon, left that black hole 26,000 years ago, when humans were living in the Stone Age, when the last ice age was ending, when we had not yet invented writing or agriculture or civilization. That light traveled for 26,000 years, crossing the galaxy, through clouds of gas and dust, past billions of stars, until finally it arrived at Earth and entered your telescope. And what was happening at Sagittarius A star right now at this exact moment, we will not know for 26,000 years. The light conveying that information has not reached us yet. It is still traveling, crossing the void. And for the most distant black holes, the quasars at the edge of the observable universe, the light we see left those objects over 13 billion years ago. When the universe was young, when galaxies were just forming, when the first stars were igniting, that light has been traveling longer than Earth has existed, longer than the Sun has existed. It left a black hole in the early universe and traveled for most of cosmic history until it reached us. And that black hole, as it is right now, we will never know. The universe has expanded so much that new light from that black hole will never reach us. We are seeing a ghost, an image from the distant past, frozen, unchanging, a snapshot of a structure that has evolved, changed, perhaps merged with another galaxy, but we will never see those updates. The expansion of space has severed the connection, and this is the final horror. Not just that black holes are large, not just that they are numerous, but that they are unreachable. The black holes in distant galaxies, billions of light years away, are fundamentally inaccessible. We can observe them, we can measure them, but we can never visit them. We can never probe them directly. The expansion of space ensures that most of the universe is forever beyond our reach. We are trapped, confined to a tiny region of space. A bubble perhaps a few billion light-years across. The cosmological horizon. Beyond that, space is receding faster than light can travel. We cannot go there. We cannot even send a signal there. Those regions are causally disconnected from us. They might as well not exist. For us, the observable universe is the only universe. And within that universe, we occupy one planet. One insignificant, tiny, fragile world, orbiting one ordinary star, in one galaxy among hundreds of billions. And scattered throughout that observable universe are structures so massive, so dense, so gravitationally dominant, that they define the architecture of space-time itself. Black holes. And we are nothing compared to them. Let me give you one final comparison. The most massive structure humans have ever built is the Great Wall of China. Including all its branches, it stretches approximately 21,000 kilometers. It has a mass of approximately 50 million metric tons. 50 million tons. The largest ship ever built, the Sea-Wise Giant, had a mass of approximately 564,000 metric tons when fully loaded. The Three Gorges Dam contains approximately 27 million cubic meters of concrete, tens of millions of tons. These are the largest, most impressive structures humanity has created, monuments to engineering, to ambition. And compared to Sagittarius A star, they are nothing. The black hole at the center of our galaxy has a mass of approximately 8 times 10 to the power of 36 kilograms. 8 million trillion kilograms. The Three Gorges Dam is approximately 10 to the power of 10 kilograms. 10 billion kilograms. The black hole is approximately 8 times 10 to the power of 26 times more massive. The ratio is incomprehensible. All the structures ever built by humanity, combined, every building, every road, every bridge, every dam, every monument added together, would not equal 1/1,000,000th of 1/1,000,000th of 1/1,000,000th of the mass of Sagittarius A star. And Sagittarius A star is modest, small, unremarkable compared to the giants. Compared to M87 star or TON 618, our collective engineering achievements are less than quantum noise. You are standing on a planet orbiting a star. The star is orbiting a black hole. The black hole is 4 million times more massive than the star. The star completes one orbit every 225 million years. You, in your brief lifetime of 70 or 80 years if you are lucky, will experience approximately 0.0003 of one galactic orbit. You are born, you live, you die, and the galaxy has barely moved. The black hole has barely consumed any mass. The universe has barely aged. You are a flicker, a spark, a momentary pattern in the chaos. And when you are gone, when your atoms have dispersed and been recycled into new stars and planets, the black holes will remain, feeding, growing, patient, eternal in practice if not in theory. This is the true scale, not just of black holes, but of the universe. Not just the distances, but the masses, the timescales, the energies. Everything operates on scales that dwarf human experience, that render human significance invisible. We are not just small, we are inconsequential, and yet we are here, conscious, aware, capable of comprehending our own insignificance. A black hole cannot do this. A galaxy cannot do this. Only you, only conscious beings, can look out at the cosmos and understand, truly understand, how vast it is, how small we are, how temporary our existence. And perhaps that is enough. Perhaps that awareness, that consciousness, that ability to comprehend the incomprehensible is what gives meaning to a meaningless universe. Not because it changes anything, not because it makes us important, but because it is rare, precious, fragile. A brief moment of self-awareness in an ocean of unconscious matter and energy. The black holes are out there, right now, feeding, merging, evaporating, warping space-time, dominating the gravitational landscape of the cosmos. And you are here, reading these words, thinking about them, feeling small, feeling terrified, feeling awe. That feeling is real, that consciousness is real. And in a universe filled with black holes, with voids, with emptiness, with structures so large they challenge comprehension, your consciousness is extraordinary. Not because you are large, but because you exist at all. So the next time you look up at the night sky, remember, every star you see is orbiting a black hole. Every galaxy contains millions or billions of them. The universe is filled with these gravitational monsters. And you are here, tiny, fragile, temporary, but awake, aware, alive. If this journey changed how you see the universe, if it made you feel the weight of cosmic scale, do me one small favor. Hit the like button, subscribe. Because understanding our place in the universe, understanding how small we truly are, is not just science. It is perspective. It is humility. It is the realization that we are part of something vastly larger than ourselves, something we can study, measure, and begin to understand, but never control, never dominate, only witness. The black holes are waiting, silent, patient, inevitable. And you, for this brief moment, are fortunate enough to know they exist.